There we go. Right. So, yeah, so who am I? So like I actually mentioned, currently working at Bastian Solutions. So that's a materials handling company here in Boise. We're actually located in Indiana, headquartered in Indiana, but we have an R&D office here in Boise. Been doing that for a little over a year. I mostly do low-level firmware and low-level software on the embedded systems team. Prior to that, I was at Apple for 3 years working on human interface devices. So our organization covered touchscreens, keyboards, trackpads, the Apple Pencil, the watch, anything you would like physically interact with your hands, and then a couple other projects. And in doing that, I worked on firmware, did a lot of test automation and quality assurance, did factory support, did all sorts of stuff working at that job. So that was pretty wild. And then, yeah, graduated in 2016 from Boise State and did 5 years in the Army before that. So yeah, so as any good presentation should, you start off with a quote from Wikipedia. So just what exactly is an embedded system, right? And so they say an embedded system is a computer system. Make sure this little like widget on my right side isn't in your guys' screen, right? I'm assuming it's not. No. Cool. Okay. It's an embedded system is a computer system. It's a combination of computer processor, computer memory, and then input-output peripheral devices that has a dedicated function within a larger mechanical or electrical system. And so, in my opinion, that kind of dedicated function piece is key right here because it says that an embedded system is a computing system, right? So it's got some sort of computer on it, but its scope is much more narrow than like your traditional computer, right? So the laptop that I'm presenting for you guys right now has like a keyboard on it. It's got a touchpad on it. It's got a screen. It can connect to the internet. I can play games. I can type things out of it, all this crazy stuff. But an embedded systems is usually much more constrained in what it does. It doesn't have as broad of a scope. It might only talk to a sensor, right, to report temperature, or it might talk to a sensor to measure, the gas level in your gas tank or something like that. So it's a computing system that's just much more limited in scope and usually limited in resources as well. But and then I personally love, I don't know if you guys seen this TLDR thing coming up. Maybe I think it's so cool because I'm like old now, but the too long did not read. I love that that's showing up in, I've seen it in emails at work right now, so I had to like put it in here. But in my opinion, the embedded systems is an army of tiny little controllers that are, controlling, or if you want to think of it the other way, enhancing your life. And so you find them in phones. Your phone has a bunch of them in it. They're everywhere in your cars, especially depending on what kind of car you have. You can have like 100 little embedded systems doing various things throughout your car. They're in agriculture, HVAC. If you were part of the senior design talks I gave a month or so ago, there was a company that put them in a juice press with varying degrees of success. If you ever heard of Juicero, you should look them up. Bike lights, one of the senior design teams is going to do an embedded system bike light for me this year. And then if you ever see IoT, there's almost embedded system definitely in there for some point. So it's just these little mini computer systems that are just sprinkled throughout your life, and you might not even notice they're there. Why does this thing do this? There we go. Okay, so in embedded systems, then there's all different areas that you can kind of specialize in, right? And so you could work as like a hardware engineer in embedded systems group where you're doing lots of like board design and layout and schematic stuff and really deep in the EE part of it. You can be a software engineer or a firmware engineer, and so then you might ask, well, what's the difference between a software and a firmware engineer in embedded systems? And so that's a pretty debatable context, but in my opinion, the software engineer is when you get into a system that has like a traditional operating system on it, right? So you might hear about people talking about like embedded Linux, and so usually you got people who are writing software there that's kind of tailored for a limited, Linux system. Firmware, which is what I do, which is a lot of talking to like low-level sensors, communications protocols, that sort of thing. A really interesting one that's kind of come up in the last, handful of years that is kind of getting more and more traction is embedded security. And so have you guys ever heard of like the Amazon rings that people put on their front door to like monitor and make sure people aren't stealing their trash cans and stuff? Has anyone ever heard of that?
Yeah, I've seen those.
Okay, I was like, am I the only one? So anyways, it's a little embedded system that it's got a camera on it, right? And it's got a little computer, and it's got, it can basically do motion detection, and it'll send you a little alert on your phone. But they had a problem where like hackers, hacked into this embedded system because it wasn't secure, and then they like started like monitoring people in their houses and talking, doing all sorts of weird stuff. So quite often with embedded systems, the security piece doesn't get as much traction as say like, banking software or something like that, right? Just because, there's less time, and, if all you have is a tiny little microcontroller, do you even have the resources to do security? So it's a really interesting piece that people are like trying to tackle right now is how do you provide security to these microcontrollers that are all over our lives now with the limited resource they have. Another really interesting one was algorithms. So when I was working at Apple, I worked on the touchscreens there. And so, you write firmware that can scan a touchscreen and, get the raw pixel values of the capacitive pixels, right? But then you have groups of people that are really specialized in the algorithms piece of that, of like, okay, given all this raw sensor data, how do you actually tell that someone like pressed their finger on that location of the screen, right? How do you make sure that, when you register that press, that it doesn't wiggle around and all sorts of crazy stuff. So that's another really interesting piece of embedded systems, is how do you process all this data, and how do you, again, do it in like a limited resource constrained environment. And then safety. So depending on what kind of embedded systems you're in, there's always the safety aspect of it. If you're working on car embedded systems, you might be working on a piece that controls the braking system, right, on a little microcontroller, but your code has to be so bulletproof and designed so well because it can't fail. So I don't have a ton of experience in that stuff, but I know a couple of people who worked in it. And then the piece that I always harp on, because I think it doesn't get near enough attention as it should, is testing and quality assurance. So you guys have all taken at least some sort of computer programming class, I'm sure, and they teach about unit testing and making sure that, when you write a function that says add 2 integers, that it actually adds them, it doesn't subtract them and all that kind of stuff. And, you can test that stuff in software, but with embedded systems, it's like you have this little microcontroller hooked up to your weather monitoring station or somewhere, right? Like, how do you actually test that to make sure it works? It's a very interesting thing to get a lot of exposure to, because it's not like you're just testing software, you're usually testing a device, and if you're testing a device that doesn't have all these fancy testing facilities, all that sort of stuff. So, but with all that said, specializations, like what kind of thing are you interested in? What kind of niche fields, embedded systems you want to do? And I would say that a lot of it just depends on where you work. And I'll get into that in slides a little further on, but there's people who are going to be laser focused and stuff. There's people who are going to have really broad experiences. But one thing I would say that a lot of embedded systems engineers that I've met, the really good ones, are ones that have experience in a lot of different things and know enough about all the different pieces that, they might not be an expert on hardware, but they can read a schematic and sit in a board review and give insightful insight and that sort of stuff. So yeah, with all that said,
sorry,
you're good.
Can you really quickly just sort of restate like what an embedded system is? What an embedded system is?
Yeah. You want the Wikipedia one or my version of it? So what I would say, in short, is like an embedded system is an embedded system is just a small computing platform that has a fairly dedicated scope of what it does, right? And so maybe I'll give you an example that might help. So like an example you might find when you Google embedded systems tutorials on the internet is like a weather monitoring station, right? That's an easy one you can do in your at home with like limited stuff. So to do that, you need a little computer that can talk to a temperature sensor over like an I2C format or something like that. To get the actual what's the temperature, you need the computer to be able to talk, UART or something, some serial protocol to like a humidity monitor, right? What's the humidity? And then, once you have that actual data, you'll need something that maybe saves it to like an SD card, or if you're using like Bluetooth, you need something that can talk to the Bluetooth chip and send it out. And so in my opinion, it's this whole device that does some sort of computing problem. It solves a computing problem that is more defined in scope, right? Like your current laptop can do all sorts of stuff. Like I said before, it can connect to the internet, it can watch videos, it can play games, it can do all sorts of crazy things. But an embedded system is usually targeted to do, like one thing or a handful of things. Does that help? That make sense?
I think that was pretty good. Does anyone else want any more clarification?
Feel free to stop me.
I guess. What about microprocessors? Are they like the same thing?
That's a good question. Yeah. So usually the definition there is like the microprocessor is the piece that consists of like the CPU and like the arithmetic logic unit. I don't know if you guys have taken computer architecture or that kind of thing yet, but the hardware piece that can like execute machine code instructions and retrieve an instruction from memory and, output the results or register or something like that. But usually when you talk about a microcontroller, it's got the microprocessor inside of it, and then it's got like peripherals on the, I say outside, but it's still within the same chip. So it's got like a peripheral that can talk a UART protocol, right? Or a peripheral that can talk Bluetooth, or a peripheral that can talk I2C, or doing analog to digital conversions. Like the microprocessor is like the brains, and then the microcontroller has that microprocessor inside of it, as well as peripherals to help it do meaningful work. Does that make sense?
So which one is in which? Is it embedded system inside of microcontroller?
So I would say a microprocessor would be inside of a microcontroller, and an embedded system would have one or more microcontrollers inside of it. You might have a microcontroller that just is the weather monitoring piece, and then another microcontroller that's responsible for logging that data to an SD card or something like that.
Okay, thank you.
Yep. Any other questions for now? Cool. Okay, yeah. So yeah, the day in the life. I don't know if you guys have ever seen Office Space, but I immediately thought of this. You know, as what exactly do you do here, right? This is the Bobs. If you haven't seen this movie, you should totally check it out. But I was thinking about this of like, okay, what do I do in a typical day at work, right? And so I came up with this kind of list of things that I think kind of encapsulate that. And so some of them are kind of goofy, but so like right now I work in an R&D department, and we're right in the middle of like a really big design and architecture of like a complex system. And so one of the things I like to say is, you know, I promote cross-functional synergy. And so like, what on earth does that even mean? And so, but the way what I'm trying to say there is, so I'm trying to design a piece of this larger complex system, right? But from what I do, which is like low-level firmware programming, I'm really interested in like what communication protocol does it use? How fast can I talk to it over that communication protocol? You know, what sort of development environment do I have to use for it? But the mechanical engineering team is going to be more interested in like, okay, well, he wants to use this motor controller to drive this motor, but that motor controller is the size of like a shoebox, and that's way too big for our system, right? Or the electrical people might be like, well, you know, that motor controller only uses 12 volts and our system is a 48 volt controller. So a lot of what I've been doing lately, and I found this a lot, is just kind of working with all the different teams to make sure that, you know, their needs are reflected in my design works with like within their constraints, that my design doesn't get too complicated because of the choices that they make, a lot of that stuff. So absolutely working with like all the other different teams in my job all the time. I'm constantly talking to the mechanical engineering team, software engineering leads, all sorts of people. And then kind of similar to that, if anyone's taking operating systems at all, there's something called like a context switch, which is where you switch from like one process to the other. So like your computer behind the scenes will switch your Zoom video app, and then it'll run like the internet browser app, you know, behind the scenes. You just never notice. That's how you can like run multiple programs at once. But what I find I end up doing a lot is switching back and forth between tasks just all the time. So for example, I was in a call earlier this morning talking about state machines for the firmware and the software, right? Like, when this robot gets powered on, what does it do? It does like a self-test, and then it goes and checks the, checks its configuration or something like that. And so it was very heavy in like the software and the controls piece. And then right after that call, I had to go get on a call with a vendor and talk to them about, you know, okay, like, well, here's the controllers we have. Here's like how big they are. Like I said before, you know, the mechanical engineering team is really interested in that. Here's how much they cost. So kind of going to that first one is a lot of switching different tasks that are maybe not necessarily just writing code or just designing a circuit board or something like that. Especially working in R&D, but I also saw this at Apple a ton, is that a lot of the time is spent just doing research on things. So a lot of things I've been doing is researching. There's like a lot of protocol definitions, like I'm sure you guys have heard of like USB and Bluetooth and stuff. That's like the protocol, which is like, how do you transfer all these bytes across, you know, the airwaves or across like an electrical wire or something like that. So there's all these different protocols for all sorts of stuff, but especially working in firmware, as an embedded systems firmware engineer, you do a lot of like understanding of how these protocols work, because lots of different chips use different ones. So a lot of reading papers on that. Kind of like I mentioned before, doing a lot of design and architecture work. And so I know as you guys go through your schooling, you'll go to senior design and they'll harp on this. And like, I remember thinking when I was in senior design, I was like, oh, these papers are so boring. Just let me get to like designing the board and writing code. But this stuff is super important. And especially once you get into your job and you find that your design choices, if you make bad ones, can cost your company time and money and that sort of thing. So I spend a lot of time whiteboarding and researching designs and talking to other people to get their opinions on it. Especially working in R&D, we do a ton of industry standards and trends, right? So we're always looking to see, you know, what are our competitors doing? What are like the emerging trends in the industry that we might want to be interested in? And then kind of going to the protocol different ones, I spend a lot of time reading data sheets. So picking up data sheets for like the microcontroller, which like might be 2,000 pages long, and going through and extracting data that I need out of there, all sorts of stuff. And then, you know, once I get done with all these meetings and all this research stuff is when the actual development happens. So depending on what you end up doing, I would, even if you're, you know, a hardware engineer or you're interested in the algorithms, like you're going to spend a ton of time just doing, you know, other design, and especially just working with other teams. I can't harp on that enough, that teamwork is super crucial in embedded systems because it's such a broad field. So, okay, so now some actual experience about kind of what I've worked on. So, like I mentioned, I worked in human interface devices at Apple. So up in the top right here is the logic board from the iPhone 10. And so you can just go to iFixit. If you guys have never seen that, I'd totally encourage you to just go there and kind of skim through some of their stuff. They buy commercial products and then like pull them apart and examine them and figure out what chips are in them. It's a really cool website. But this is the main logic board. This is one side of it. So I didn't work specifically on this, but I can tell you that there was tons and tons of embedded systems engineers who did. So there's probably a whole team of people that worked just on this board design. So you notice there's, you know, the A11, which is your main application processor. That's the thing that actually runs iOS. I don't even know what all the rest of these are, but there's a chip that does like your cellular modem. You know, there's a chip that does your touch screen. There's a chip that controls Bluetooth, all sorts of stuff. So, you know, there was a whole team of people that was good enough at board design that they could design this tiny little board and fit everything on there. There was a team of embedded systems engineers that wrote the operating system that runs on this A11 thing, so iOS. There's somewhere on here, there's a security chip that's like the root of trust for the whole system. And that's the thing that keeps all of your secret keys confidential and makes sure that, you know, the NSA can't track your data and all that kind of stuff. So there's a whole team of crypto experts that worked in this piece, but
how big are those teams?
It really depends. So in human interface devices, the firmware team that I worked with, I think we were like 4 or 5 people that were just working on phone-ish. And there's probably a comparable team that did iPhone or iPad. So that's what I would say, just for people doing firmware. Then there was like a whole other team that just did software, kind of like higher level software that still handled like touch data. The ALGS team was probably similar in size. But then, you know, when you get into like these other teams, I can only speculate, but I would say that they're easily comparable in size. And then let's see, yeah. And so, yeah, so you know, all these teams that do all these various things, like there's the board design team, firmware, security, algorithms, like all of those, there's definitely teams for every single one of those I mentioned that were, you know, in some way handled, you know, one or more pieces of this thing. So yeah, I would totally encourage you guys to just go check out iFixit. I just kind of like looking at their stuff when they pull it apart, because it's just like, man, like it's crazy how much stuff they fit in such a small space. And then down at the bottom right is, yeah, again, the iPhone 10. And so, oh, one thing I didn't mention about that. So, you know, we're doing firmware and software and all that kind of thing. There's also, you know, mechanical engineering that goes with it. And like, this is not like maybe embedded systems, but it's one of those kind of like peripheral things of like, you know, just because they're not writing code, you still had to, you know, you still worked with them. You still need to know what they were doing. It was just kind of that, like, what I'm trying to look for here. It was kind of, you know, all the cross collaboration between all the teams. Like you didn't just do your one job and sit in a bubble. You were definitely working with all sorts of other people. So, so some kind of key takeaways working with these teams that I thought was really interesting is, you know, at Apple, you're laser focused on like what you're doing, very high in the specialization. So, you know, you have someone who is so dedicated to the touch algorithms that they're, you know, like world-renowned experts in that kind of thing. And like, you know, they could write, I think they do actually now write papers on it. And, you know, they're the, like I said, the world-renowned experts in this sort of thing, very high specialization. For firmware, it got to the point where like, they're very extreme in their optimization of this. If you've taken microprocessors yet, I'm sure you've seen some assembly, and you know, maybe you've heard that, yeah, no one uses assembly anymore. But I knew multiple firmware engineers that did handwritten assembly to make sure that their code ran fast enough and was, you know, hitting their timing deadlines. So that's the kind of level of, I guess, like technical expertise these people had. Another thing that was really interesting about this is, you know, you start thinking about like timing. So for example, like how long does it take to scan a touch panel to find out like, you know, where your fingers are and all that sort of stuff. There were engineers that could tell you like down to the microsecond how long it took to run certain portions of the code. So very, very deep in the knowledge. Again, another firmware-ish thing, you know, obviously not every embedded systems person does all firmware, but that was my background. So the, you know, like when you build your software, right, you hit Java C if you're building Java, or you use GCC if you're building C code. you get this binary blob of data that's, ones and zeros at this point. But these folks were so into their processes and knew exactly what was going on that they could tell you the number of bytes that they had left in their processor, and they had full knowledge of their build process. So basically everything they did, it was like 100% deliberate, I guess. And the reason they do this is because when you build, it's not just true just for iPhones, it's true for any consumer electronic. When you build millions of these devices, if you have like a 1% yield loss at the factory due to a firmware bug, right? Like 1% of the iPhones are reporting failures because the touch controller says it has a voltage brownout or something like that. You get called at Saturday at midnight and you have to deal with it immediately. So Apple needed their engineers to be subject matter experts on whatever they were doing. So I guess in summary, they were super laser focused. Industry leaders in their fields knew exactly what they were doing, and had 100% control over everything. So it was a very, I don't want to say brutal, but it was a very fast paced, and like you had to be 100% on it to succeed there. So it's pretty wild. And then again, just to harp on it, the testing and quality assurance piece. So when we were working on iPhone 10, just to kind of give you like a level, like a glimpse at like what kind of testing goes on, we were working on touchscreens. We literally built a robot that all it did was just turn the touchscreen on and off and made sure that the touch microcontroller, woke up and booted correctly and didn't have any weird errors. And we used to do that, 100,000 plus cycles was not an uncommon number to see. And we had multiple robots just doing that all the time. It got to the point where our test software that was running Python on like a normal computer was more likely to crash than the phone was. It was like kind of like the crazy level that we used to test things at. And then I stole this picture from Info Security, but it's you're looking for a bug in the binary data. But one thing working in embedded systems is that it's not uncommon to have to look at, I don't say binary data, but like hexadecimal data, like logs, and just see, you're down to the level where there's not much abstraction below you, right? You're deeply into the hardware of your device, and so looking at hexadecimal and sometimes binary data is not uncommon, and I still do it fairly often. So just more fun things to learn how to test. Okay, so now, so a little changing here. Go ahead.
Can I ask you a quick question? So I understand how you can debug a program, because if you messed up, let's say logic in your program, then of course you have to fix the logic. How do you mess up, or like how does the code mess up the binary like ones and zeros? I don't see that in my mind.
So an example here, I'll give you an example. So if you've ever done any like communication protocol stuff, right? Like say for example, you're using Bluetooth, and I've never done Bluetooth, so I'm going to make some assumptions here, but let's say you have 4 bytes of data. That's your temperature data from this like weather station embedded systems you're building, right? And you're going to send that data to your phone via Bluetooth. We're just making general here. So you might have, when you get ready to send that data, and this is one of the things about embedded systems is this abstraction piece I was talking about, is there's really not any abstraction below you. You have to know exactly what's going on. So when you get ready to send that data, or before you even send it, when you collect that data in your firmware, that's a chunk of memory somewhere. That's 4 bytes of data. And you don't know exactly what was there before, right? You might have booted up the processor and it got zeroed out, or it might have been a previous 4 bytes of temperature that was something else, or it might be, I don't know, something crazy. But basically it's an unknown value. And so if you don't basically clear that, well, let's assume it's bigger than 4 bytes. If you don't clear all the data to make it zeros before you put it in, you can have like remnant data there. So like if you have a buffer of data and you want to use 2 bytes of it, and you don't clear it all before you assign to it, you can essentially have kind of remnant data, if that makes sense. And so that's an example I've seen more than once where, you're reusing this chunk of memory, but before you use it, you don't clear it out to zeros, and then you store partial data there. You kind of have the remnants of whatever was there before. Does that make sense? It's kind of a hard example without actually showing it on like a logic analyzer or something, but hopefully it made sense. It's essentially, you get whatever was garbage was stored there before.
Yeah, should be good. Thank you.
Okay, yeah, no problem. Okay, so the next kind of examples, now that I've been, we're talking about Apple a bit. So like I said, I'm working in Bastian Solutions right now, doing materials handling stuff. And so, what exactly is materials handling? Because I didn't know either until I started looking at this company. But I kind of view it as like, it's the secret behind the 2-day, Prime delivery from Amazon. So like when I go on Amazon Prime and I'm like, hey, I want 5 pounds of gummy bears, a bike or a thing of chain lube for my bike, and like a new pair of pants because I'm going to eat 5 pounds of gummy bears. That's the thing that's going to be able to get me those random 3 items, you know, from some warehouse somewhere to my house in 2 days. And so on the right there this is like a mock-up of one of our concepts that one of our group in our company did of one of these like crazy distribution centers. And that's one of the things our company does is, you know, people like, who I was looking for? Chewy, which is like a dog toy company or something like that. Best Buy, companies like that say, hey, I want to make a new distribution center or a warehouse in some state. And, you know, this is the kind of product we're going to move through it. This is how much we're going to move through it. Like, help us design something. That's what my company does. And so if you see on this picture, they've got, you know, a whole bunch of rack, you know, 40, 50 foot tall racks. And then you've got some sort of conveyor here. And this is probably like a tote section where essentially they keep like loose items in like boxes, and then a robot will come through and like grab an item from it and put it, you know, in a box to get delivered. So anyways, it's all about designing, you know, what is the most optimum way to store all this random stuff that consumers want to buy and get it pulled out of these storage locations, packaged and shipped and routed, and, you know, and managed of like when it's leaving the facility and then actually shipped to their home. So it's a really interesting industry, and I never really heard about it until I kind of started working there. But from an embedded systems perspective, it's like, you know, what does that have to do with it? And well, when you think about it, you see these blue things here, which are these conveyors. A lot of these conveyors are powered, right? And so there's a little motor on the roller there that actually spins and pushes the box along. So you have a little microcontroller there that drives that motor, which might seem, you know, oh, it's just driving a motor. That's not complex. But when they get into this point, it's not just like driving a box down a conveyor. It's like, hey, sometimes you need to hold that box there until 10 other boxes show up behind it and then send them all out at once. Or there's something called zero pressure logic, which is like basically keeping the boxes from smashing into each other if they have like, you know, maybe you're sending bottles of wine across the country, right? Which is one of the things our company does. And so there's a lot of complexity you never really think about until you start looking at how do you optimize these crazy problems. There's a lot of sensors in here. When, you know, when a box is moving on a conveyor, you know, it needs to have its barcode read to say, hey, yeah, this box left the facility and it's on the truck. Or it needs to go across the weight sensor to say, yeah, this box weighs 10 pounds and that's what we expected it to weigh. Or, you know, no, this box weighs 100 pounds and it should have weighed 5. Like, what is the, you know, what extra is in here? So there's a lot of little hidden embedded systems that kind of go in with materials handling. And so specifically for research and development, some of the stuff that we work on, so up here on the right, you can see it. This is the biggest picture I found, unfortunately, but this is our kind of rack and shuttle system we're working on. And so if you can look closely, it's these kind of vertical racks of totes. And so again, imagine a bunch of little, kind of usually a little bit bigger than like a shoebox, totes that kind of line up all along here and have different stuff in them. So you might have like Pringles cans in one and then like tube socks in another or something like that. And these robots will actually get orders, right? So Sean ordered his 5-pound bag of gummy bears, his bottle of bike chain lube, and his new pair of pants. And so these robots are smart enough to go drive into this grid and go up and down the different levels and find the thing and pull one out, put it in their little tote, come back out and send it to my box and send it to me. So we're specifically working on the shuttle system there. And so that's got a bunch of different embedded systems in it. You know, it's got stuff to control the motors. It's got stuff to control this robotic arm, which is another piece that we've been working on. It's got stuff to control like the tote extraction, all sorts of different crazy stuff, but multiple embedded systems involved in there. And again, kind of as I harped on before, whereas at Apple, we were very specialized in what we did. At least in my current position, I think a lot of it is just R&D, but it's extremely broad in scope, right? So I mostly do firmware and low-level software, but I've definitely stepped in and worked with the hardware team on things. I've been working with the security team on some other stuff. Really interesting one, especially for arms, is like motion control. So if you look at this arm here, I believe it's got 6 joints in it. And so when you tell that thing of like, hey, reach into the bin and grab Sean's tube socks out of there, you have to tell each one of those little embedded systems, which are kind of, you know, isolated. You have to tell each of them to move basically in sync so that the arm like actually moves down and grabs my tube socks and doesn't smash into a wall or something. So there's like a whole level of that algorithms piece I was talking about that kind of goes behind this. Another interesting one that's kind of come up, and not just here, but elsewhere as well, you guys might have heard of, is like the edge computing piece. And so that's like, you know, with all these microcontrollers getting better and better, and like Raspberry Pis coming out that like are the size of a credit card, it's like, well, we can do crazy new computing, like machine learning and AI and stuff at these kind of edge pieces, like the sensor pieces. And so that's something that our team has kind of been looking into a bit. But yeah, I think the last thing I was going to mention here, and hopefully I kind of conveyed it, but like an embedded systems engineer, it can be a lot of different things, right? Like you might be a hardware engineer, you might be like me and be more firmware, but the two pieces I've found that have helped me be successful is make sure you've got something that's helping you increase your skills, right? So I'm really interested in the firmware piece. And so there's a couple different blogs, the Interrupt blog and the Embedded Artistry, that are really great. They write articles all the time. And I'm not sure, I'm still trying to figure out why this is, but the number of like book resources for embedded systems is a little bit limited. There's nowhere near as much as if you were like, wanting to learn JavaScript or something like that. So finding a way to make sure that you're continuing your education is super important. And then just being able to broaden your horizons a bunch, even if you're, whatever niche you find yourself in, kind of like look to your left, to your right, and see the other engineers who work alongside you in that embedded system, and make sure you at least kind of know a little bit about what they do, right? So that, you can work better between the two of you. And if one day, if you have to step into their shoes and work on something, then you're kind of already ready to do that. So anyways, yeah, that's kind of all I had. Did you guys have any questions?
So on those robot arms, do you have to control every servo individually, or do you have a program that controls all of them as one unit?
Yeah, so usually the latter. And you can,
okay.
If you want to see it, there's, if you're interested, there's, what's it called? In the CAN Open, there's a protocol called DSP 406. But anyways, yeah, to your point, it's all kind of in synchronized motion. You kind of send all of them, hey, this is your next position to move, which usually means like, you rotate this much, and this guy rotates that much, and this guy rotates like this, and then it tells them all to go, and then they all kind of move at the same time.
Oh, okay. So is it kind of like the FANUC robots?
I haven't seen that one. What was it called? The Fantic?
FANUC. Sorry, it's
Let me see here.
Those were used for like industrial, like auto parts.
Oh, cool.
If I remember correctly, but
Let me see here.
I'm just curious.
Yeah, actually, those look like, I'm sure they're using similar concepts. Those are much beefier, bigger versions of this, but yeah, it's the same general idea, right? Like if that robot wants to come in and like weld a joint on the car frame, it's got to make sure that it gets there correctly and doesn't smash into a wall on the way or miss it or something like that. So there's a whole specialization related to this stuff. Yeah, making sure it works smoothly, like reducing the vibration and like all that kind of stuff. So when I first heard about it, I was like, oh, okay, you just tell them to all move at the same time. And then you start talking about it, you're like, no, it's way more complicated than that. Yep. So
cool. Thank you.
Yeah, no problem. Who else has questions?
I have a question.
So
I understood that you went directly from Boise State to Apple. Is that true?
Yeah. Yeah.
Did you have any prior experience, or did you feel like you were adequate enough that your knowledge was, how did you know that you were ready to just go straight to like Apple?
Interesting. Yeah. So when I was at Boise State, I did 2 internships at HP here in Boise. I worked on the R&D electrical engineering team. So I did like board design and circuit schematics and stuff, which I've enjoyed, but kind of as I was going through my schooling, I realized I was a little bit more interested in like the firmware side of things. But yeah, to your second point of like how I felt when I got there, I was, to be honest, I was a little nervous. I was like, oh my gosh, am I gonna like succeed, or am I gonna like crash and burn, right? So I think I would say that, a good employer when you come out of school realizes that like you're not coming out, like you're not the world-renowned expert in things, right? Like they're gonna have to teach you some stuff. But I think what made me successful was I was willing to like, go off and learn that kind of thing. So for example, like, I tried to make it so that, my mentors at Apple didn't need to hold my hand and like teach me every single little thing. I tried to be as like, go off on my own and learn as much as I could. So yeah, to your question, I would say I was totally terrified that I wasn't going to be up to the task when I left from Boise State to Apple. But when I got there, like, the team I worked with was really great, and every great team I've worked with has been like this, where they don't expect you to be an expert in it. They just want to make sure, they just want to know that you're willing to learn it and you're willing to put the effort in, that sort of thing. Does that help, or does that answer your question?
Yeah, 100%. Thank you.
And going off that, how long did it take you to get to the point where you were contributing more and didn't need, I guess, the training wheels?
Yeah. I would say probably the first year-ish was pretty heavy on, making sure I wasn't screwing things up. I had a pretty regular habit of kind of like talking to my mentor and be like, hey, this is what I'm working on. This is what I think the right approach for it is. This is where I want to move forward. Does this make sense to you, to kind of make sure that I wasn't going off on the wrong path? But I think after the first year-ish, I learned enough that, like, I still was not an expert, but I knew enough that I wouldn't screw things up too badly when I went off on my own. So about the first year-ish for me was, you know, it was still the point where, like, you know, I was making sure that my mentor and my manager had updates, and they were giving me feedback and sometimes telling me, hey, this is the exact thing you need to go do. But it was the point where I wasn't nearly as nervous about doing things on my
own. Corbin put a question in the chat here. He wants to know if you've gotten to do a lot of traveling in any of your jobs.
So when I was at Apple, I didn't do any traveling for my job. We knew people. I knew a bunch of people that went to China for like the iPhone builds. So that's another piece of embedded systems I don't think I talked too much about, but like a big piece of it is the manufacturing piece, right? So when you want to make 1 million iPhones, you know, your design has to lend itself to a factory setup and a factory test procedure. So I knew people who went to China to help support those builds. I never got to go. I was a little bit disappointed I couldn't get to go, but never did that. My current job is really big on going to conferences, kind of that piece of like making sure that, you know, we're at the edge of the, you know, the leader of the industry, and we're not like doing stuff that someone already solved a year ago. So they're really big on us going to conferences and learning new things. That being said, with COVID, that's pretty much been canceled this year. So I haven't gotten to do much travel yet for my job. I'm hoping to once, you know, all the COVID stuff gets under control, but we'll see. So
it sounds like it's still something that embedded systems engineers do get to do that.
Yeah, and that would be one of those ones. I think it really depends on what you do. Yeah, like at Apple, it was like you really only traveled if you needed to go to support one of the builds. R&D, they want us to go to a lot of conferences. I think if you work in like a shop that does embedded designs for like separate clients and customers, you'll probably be traveling to their sites and to their offices more and more. So I think it depends on what you end up doing, but yeah, there's definitely potential there. What else?
Hang on, there's a, let's see. Which languages for embedded programming are popular right now, or are of interest in the future? Is like C, C++, Rust, are those?
Yeah. So C is still, I mean, I've only been out of school for 4 years, so you know, I'm not like the, you know, world-renowned expert just yet, but from my experience, C is the de facto standard of, especially at microcontroller level, what you're writing. And you know, like I said before, you might see assembly peppered in there occasionally, but that's a little bit more specific to what you do. C++, yep, definitely. So we use ROS, the robot operating system, at our work a lot for some of the robot level stuff, and that's either C++ or Python. So they've been trending towards C++ just because it's faster. But I also know people who've done C++ development on microcontroller. I've never done it. And then I have heard a bunch of stuff about Rust. I've actually been wanting to go check it out a bit because I've heard a lot of things about it, but I haven't found the time. So yeah, I'd say those are all on point. I've never heard of Zig, so I'm gonna have to look that up.
Excuse me.
You're good.
It sounds like it's all script languages. That's all it is, pretty much, the majority. I don't know about Python versus object orientation languages.
So you mean Zig is a scripting language, or?
No, I meant C is a script language.
Oh, I see. I'm thinking script from like Python scripting. Yeah, you're talking about like as opposed to object oriented.
Yes.
Yeah. Yeah. So what's interesting is you can do object oriented type things in C, but it's nowhere near the level. But yeah, you're correct. And I think mostly that's just because usually, unless you get into like the software end, you know, things like malloc are generally frowned upon in low level firmware because it leads to bugs and that sort of thing. So that's why object oriented isn't nearly as isn't used as much. But, a lot of it just depends on what you do. Yeah. I finally figured out where the chat thing is here. So what types of devices?
With,
yeah, looks like I found it. Okay, so what types of devices you worked on developing firmware for? So, so at Apple, it was either the microcontrollers that controlled the touchscreen, or we did some internal firmware development for some like test automation stuff. And then at my current job, it's a lot of, without getting into specifics that are like, you know, NDAs and all that sort of things, it's a lot of stuff for like doing motion control. So like motor drivers, The big one I do, honestly, so much, it's not supposed to so much of a device as it is just a feature, is like communication protocols. And so like, I know I mentioned like an embedded systems is like, you know, a small computing unit that has like one microcontroller in it, but you can absolutely have an embedded system that has like 10 microcontrollers in it. And like, they need to talk between the two of, you know, between themselves. And so a lot of what I've been doing recently is just kind of firmware that allows different microcontrollers to talk back and forth via, you know, different protocols, whether that's like, I don't do Bluetooth, but that's a good example because it's something everyone's heard of. We do a lot of CAN stuff. How much math is involved? Yeah, I don't do a ton of math unless it's like algebra level stuff. I haven't done a differential equation. I haven't done any. The algorithms guys at Apple, they were like PhDs in applied math folks. There was one guy, an astrophysics. So if you get into that algorithms piece, there's definitely math involved. It's a lot of digital signal processing, image processing, depending on what you do, that kind of stuff. So a lot of heavy math there. I'd say with motors, especially because we do a lot of motors with robots, there's a lot of math there. It's a different type of math, I guess, but yeah, that's where I'd say the biggest pieces are, is if you do any sort of like sensor interaction and you need to do data processing on the sensor, there'll be some math there, or like motor controllers are big on math. What can I do as a student and prepare for working as a embedded system engineer? I'd say, even if, okay, so I'll answer this in a couple different ways. I would say take additional programming courses, even if you think you're like, hey, I know I don't want to do the firmware, I just want to do board design. I would at least try to take a C programming course, just because your firmware engineer is going to be writing in C. And I think the additional programming it's useful kind of like sidebar knowledge, right? So if you're in the meeting with a bunch of software and firmware engineers and they're rattling on about C and everything like that, you can kind of keep, you can kind of stay on topic with them. I would also say the opposite of, you know, you're like, oh, I want to just do firmware and software. That doesn't mean you let all your normal electrical engineering stuff fall off the wayside. You know, you have to make sure you take your courses seriously and take side courses if you want to. But that being said, just in general, I'd say, you know, any extra computer engineering courses you can take. So like computer architecture, if they offer embedded systems, that's a great one, of course. All those courses would be super helpful. And then the hardest one, which is just so hard because, you know, you guys are students, I know. I remember there's like no extra time to do things, but try to find time in your spare time to do little mini projects at home. Even if that's just like, you go buy, you know, a Raspberry Pi and you make a weather station just following someone else's tutorial, that like experience is super valuable because it teaches you a lot of like the stuff that they just don't have time to teach you in school. So I'd say just, you know, take extra courses that are related to embedded engineering, and then try to find some time in your spare time to kind of do little tutorials, little projects on your side at home.
Which, speaking for the IEEE branch, that is something that we are trying to do, is sort of make events where we're focusing, like, say, on Arduinos right now, what we're probably going to do, where it's ongoing projects. So hopefully cool. All of you will be interested in that. Yeah, that's awesome. And that's super useful, because then you can go into a job interview and they can ask you like, hey, what sort of experience do you have? And, you know, you've already like, hey, I can talk about this project, and we can talk about how I wrote code to talk to sensors, or we developed our own little printed circuit board or something. So those kind of projects are super, super useful. What kind of boards would you recommend using for projects? So I'm a little biased on this one. You mentioned Arduino. I think Arduino is a good tool for sure. I would, if you've never done anything, it's a great place to start. But I would also encourage branching out into some of the other boards. So there's the Raspberry Pi, which is a good one, and like BeagleBone, if you're wanting to do something that's a little more compute heavy, right? Like they can drive HDMIs and all that kind of stuff. But if you're looking for just more typical like firmware embedded system stuff, any of the major manufacturers, STM Microelectronics is a really good one. We use them a lot at work. They've got some great development boards. Was the other one I was thinking about the other day. Nordic is a good one if you want to do like Bluetooth and cellular stuff. And the really cool thing about these companies is a lot of them have like these development boards you can get for like $10 or less sometimes. I mean, they have more expensive ones, but they have really cheap ones too. And then they'll have like example programs of like, hey, how do I get this thing to just blink an LED, right? Because that's usually like the biggest barrier to entry is like, how do you build the code and flash it on this thing? How do you just work with it? So they almost always have example code, an example like device drivers to work with this stuff. So I'd say, you know, Arduino is great to start with, but don't limit yourself there. Definitely look for other things. Yeah, STM, Texas Instruments. If you guys have specific questions or want specific recommendations, I can send out a list of things I would look at.
And then, yeah, where do you find these tutorials? Yeah, these can be kind of hard because there's not like books of them around, right? So those ones that I mentioned before, yeah, the interrupt blog, I'll just click this. So this is a company called Memfault, and they have like some commercial software stuff, but this is a very specific blog that's much more interested or much more related to like firmware and software, but sometimes they have hardware stuff on here. But this is a great blog for things like you probably won't have time to learn in school just because it gets into it. So I would definitely look for these guys. They send out this awesome, what we've been reading in the current month newsletter. And you guys can still see my screen, right? I'm assuming you can. Cool.
Yes.
Sweet. Where they go and like they scour the internet for you for all these kinds of tutorials. So we mentioned Rust. Someone's got insights on writing embedded IoT app almost entirely in Rust, and they go through, oh, these guys embedded artistry, yeah, these guys are good too. Where they go through, this whole shebang. They've got code examples. They probably have hardware in there at some point. So Interrupt is super awesome, and they weren't around when I was in school, which was always hard. But then I just discovered in the last couple of years. So I'd highly recommend any of you guys who are interested in firmware software. This one should be on your mailing list. Anyone's interested in hardware, I'd still check it out. Yeah, embedded artistry is another good one. Again, a little bit more kind of firmware and software oriented, and some of their stuff is behind paywall, so not everything is free, but they've got some good stuff. And then All About Circuits is another really good one that does all sorts of different things. They'll have firmware, they'll have software. They have like, yeah, effective MOS 9 idealities on VSLI circuit reliability. Okay, so maybe not embedded systems, but they have more than just firmware and software if you're interested in hardware or something else. So another great website. But I would say those three are really good to start with. Hackaday is also really good. Adafruit is good. Yeah, definitely check those out. If you guys want more examples, I can put together a better list, but they would be really good ones to start with. And then if you do get a development board, they always have the example code to start with too.
Right, we can probably talk with you and send that out to our members.
Yeah, definitely. Just let me know.
Okay.
I'm going to copy those links in the chat. All right. Any more questions?
Yeah, I have one. So I would assume that in Apple, you guys are picking and choosing, since they're a little bit bigger of a company, they choose what components, what microcontrollers they want on their board, whereas where you're working at now, Bastian Solutions, I would assume, because you were saying earlier, I remember you said that when you were talking to clients, you would give them a list of the embedded systems that you do have.
Yeah.
And they're certain size. Like, do the boards themselves, like when you're designing things, are you disabling certain things because you find that you don't really need all the components on the board? And
interesting.
Like,
yeah, so that's a good question, and I'll answer. But I want to bring up another point as well. You mentioned, so like at Apple, like you said, it's such a big company, and they have such a buying power that they can like customize everything down to like the smallest detail what they want, right? So they'll build their own chips from scratch, or like they'll talk to some, STM as a microcontroller vendor, like, hey, we really like this chip you have, but we want these extra peripherals added. And like, they might actually get it added, right? Like no other company has that ability. Well, Google and Facebook and this kind of probably do too, but so like they have that level to be super kind of precise and like extremely optimized and only have whatever they need. But like you said, at Bastian, we're not quite at that level yet. So to answer your question, we do end up doing that kind of stuff to some point where we have like a controller that maybe doesn't have or has more features than we need, and so we have to disable some or something like that. But one thing I think that's really awesome about our team is that we've got several engineers that are really, really good at board design. So there's a couple folks that used to work at Hewlett Packard here in Boise that came over, and they're top notch at this stuff. So when we have a need to make our own custom board, usually we can just put whatever we need on it, right? Like if we're like, hey, we're going to use this microcontroller and we want these two temperature sensors and then this motor driver and whatever else, we can go to that level and we can actually make those custom boards ourselves. But then to your second point of when we're talking to vendors, right, because we don't always have all the time to make everything ourselves, yeah, we do kind of run into that point of, hey, we really like everything you've got here, but there's like something that's missing, and so we got to find a way to put that in through somewhere else in the system. Or hey, we like this one, but it's got a couple extra things that are overkill and we're paying extra price for something, but it's it's what we work with. So yeah, there's definitely the trade-offs of when you're not at like the Apple or large other tech company buying level, where you kind of have to make the trade-offs of, okay, well, the perfect world, this is the system we want, but this is the system that we're going to have, and it's 95% of what we want, and we can fix the rest in software.
Okay, thank you.
Yep. What else? Any others?
We have one more in chat. How do you improve communication skills?
So if you mean communication skills, like just kind of like talking to other engineers and that kind of thing, or like doing interviewing and that kind of stuff, I would say just the easiest way is practice. Which, you know, I remember when I was first going through school and you have to do like your presentations in English class and that kind of stuff, that it's like super nervous and like you always feel like you're doing a bad job, but you just got to get out there and just, you know, have a practice at it and get as much, even if you're bad, just get as much practice and good feedback as you can. And so, I see one more question. So like, for example, you know, you might be wanting to focus on your communication skills for like job interviewing or something like that, right? Which I still struggle with job interviews. They're super stressful. Like a full day interview for a job, like I'm always exhausted afterwards. But just talking to your other friends, seeing what kind of job interviews they've been through, having them ask you those same questions. If you're not using the Career Center at Boise State yet, I would totally recommend it, because I'm pretty sure they used to, I'm sure they still do. They'll do like sample interviews. You can go in there and show them your resume, and they'll give you like a generic interview, even if it's not like fully tech related, right? Like when you interview at a tech company, you're gonna have to interview with the HR folks. So I would totally take advantage of the Boise State Career Center. They can definitely help you out with that kind of stuff. But I guess my suggestion is just it's all just practice, getting as much practice and good feedback as you can, and then just continuing to kind of improve on that. So, and then does Bastian have any internships? I don't think we have any right now. We're kind of in the middle of our fiscal year, so there's no money, I guess, put aside for him right now. That being said, I would not hesitate on the opportunity. I hope we're going to be at the career fair, even if it's virtual, but I wouldn't hesitate on the opportunity to, you know, if we're at the career fair, however they do it this year, you know, make sure you've got your resume updated and you can send it to us. And that goes for any company, honestly, not just Bastian, but just because there's no internships listed, don't use that as don't use that as a reason to not get yourself out there. I've seen plenty of opportunities where someone was like, wow, that was an amazing person we just met. We don't actually have a resume or a rec open, but let's get one open so we can grab that person before they do. So yeah, so I don't know if we have any internships right now. I'm gonna guess probably not, because it's kind of middle of the year, but I definitely would keep looking out for that kind of thing. We have the Bastian Solutions website. You can search it by Boise, and it's usually pretty up to date. But yeah, definitely keep an eye out for us at the career fair. Cool. What else?
Hey, Sean, I'm just jumping in and out. Sorry, I've been.
Hey, Dr. Lou, how's it going?
Good. Too many things happening today. So, are you happy at Bastian or versus Apple?
That's a good question. So I won't say that I disliked Apple. There was some great experience there. Like I said, some of the tech you see there is like you're never going to see anywhere else. It's kind of crazy, you know, growing up in Boise and then moving to the Bay Area. You know, it's quite the culture shock. That being said, I think when I left, I was ready to try something different. The Apple culture, kind of like I was talking about before, the Apple is so, you know, they need their engineers to be laser focused that I was trying to switch to a different job and basically run into the bureaucracy associated with that. So I wouldn't say that I hated it there by any means, but it was, I was ready to move on to something else. So that being said, at Bastian, I'd say I'm more happy at Bastian because, you know, with the R&D environment, if there's like a new project or a new idea I have, if it's a legitimate idea, I can take it to my lead and say, hey, look at this cool new, you know, whatever I think we should build. This is how it fits our business case. This is why I think I can do it. Or like, this is the, you know, skill I need to go learn to work on it. And I've done this before. And if it's like a reasonable request and it fits all that kind of stuff, our leads and our management is really good. And they're like, yeah, that sounds amazing. Like, get working on it. What are you waiting for? So Apple was definitely a cool opportunity, but yeah, I'd say in the long run, I'm probably more happy at Bastian now.
I got another crazy question for you.
Mm-hmm.
Throughout all these years, some of you guys may not know, this is my year number 18 at BSU. I have always believed in it is not what you learn in the classroom is going to get you the job. It might as well be what you learn in other things that is going to get you the job. Do you agree with that?
Yeah, I would say what you're going to learn in your engineering degree in the classroom is like the bare minimum, essentially, knowledge to get you to the point to learn what you really need to learn, right? And so that's why, like getting an internship and like getting that outside experience and going on, even if you don't have an internship, finding a way that you can go and do some like projects at home, essentially developing that skill and that desire to like improve on the knowledge you already have is what's going to make you a valuable engineer. Because yeah, like Dr. Liu said, what you learn in school is it's the base level you need to get to the point of actually learning what you need to do at your job. So yeah, I'd agree.
Wait, I took out all the time for question. And then remember, I should have charged you when you took a seat in my lab.
The secret story about my embedded systems, I guess origins was Dr. Liu has this awesome embedded systems lab. If you've never seen it, I would highly encourage you to go bother him about it and make him show you. But he was gracious enough to allow me to use a seat in his lab in our senior design year so we could work on our senior design projects. But yeah, and that was one of the places where we used to talk with like Vikram and Michael Pook and the other embedded systems guys. And like Dr. Liu was saying, we were learning stuff outside of class in his lab that was essentially, giving us those skills to be successful elsewhere. So, but yeah, you should have charged me to use your lab.
Yeah, I know. Well, I should have charged you based on percentage on the future earning. Maybe a percent will have lead to my millionaire status.
Well, I was working in California, so I got taxed way too hard to give you any money from that. So
just left there.
Yep. Cool.
That's all I got. Sorry, I gotta. Hey, thanks for doing this for them. And
yeah,
I got another thing another call I gotta jump on.
Cool. Yeah. Well, thanks for dropping in, Dr. Liu. It's good to talk to you.
All right.
Yes, thank you for dropping in.
All right.
Nice to see you.
Yeah. Which seriously, if you are interested in embedded systems, Dr. Liu is definitely the person to talk to. I mean, there might be other people at Boise State now, but when I was there, he was definitely one of the subject matter experts. So. Cool.
I'd definitely give a shout out to anyone for looking into any research opportunities at Boise State. Dr. Liu is awesome. I know there are lots of other professors that have their research labs going on that you might not know about. So, and it's a really, really good way to get a step up.
Yep. Absolutely. Yeah. So it's going to be one of those things that's going to differentiate you from everyone else, is being able to say, hey, I've got this internship, or I've got this research I did, and like, here's how cool it was and all the great stuff I learned. So yeah, 100% on that. Cool. Well, right on. Well, thanks for having me, guys. I appreciate it. Hopefully it was useful. I'm all for embedded systems, so definitely, hopefully this encouraged you to pursue this path.
And I think this went great.